Assalamualaikum warahmatullahi wabarakatuh and a good evening to TS Dr. Muhammad Haikal Ismail, our beloved lecturer. So today we are from group 14 would like to present about thermodynamic web. Okay. So before we go into the details, my name is Muhammad SYAHMI AL-NAQIM bin SHAMSUDIN. My metric number is 203128. Okay, let me briefing to you guys a little bit about thermodynamic web. Okay. Why do we need thermodynamic relation? Okay. Actually, this thermodynamic web, we want to develop relationship to relate the changes in the fundamental and derived properties in terms of the measured properties that are directly accessible from laboratory measurement. Okay. These properties arrive from the first and the second law of thermodynamics. Okay. Also, why Maxwell relation is very important. Okay, this is because Maxwell using the equation to propose that light is an electromagnetic phenomena. An important consequences of Maxwell equation is that they demonstrate how fluctuating electric and magnetic fields propagate at a constant speed in a vacuum. We also need to know that every properties in thermodynamic webs are related to each other. This is because thermodynamic properties such as temperature, pressure, volume, and entropy are related to each other. Their mutual relation are called property relation or Maxwell relation. And the equations showing property relation are derived from the differential form of thermodynamic potential. Okay. So next, AISHAH and IZZIYAN will explain to you guys more details about the thermodynamic web.
The change in any intensity thermodynamic properties of Z can be written in terms of partial derivatives of the two independent intensity properties X and Y, which is this one. The following relation is also true, this one. For the measured properties of the system of P, V, T, and composition, the fundamental thermodynamic properties are U and S. There are also derived thermodynamic properties, one of which is at H. There are also two other convenient derived properties, A, which is Helmholtz free energy, and G, which is Gibbs free energy. The derived thermodynamic properties have the following relationships, which is this one. Also recall the heat capacity definition, which is this one. For the fundamental property relations, first law of thermodynamics states that this one, for enthalpy, dH equal du plus dPb. For Helmholtz free energy, dA equal du minus dTs, and Gibbs free energy, dG equal dH minus dTs. By writing a number of unit relationship of certain value constant, we can yield this one. The Maxwell relation can be derived by applying Euler's reciprocity to the derivative of the equation of state. The Euler of reciprocity is this. This mathematical relationship allows one to derive what are called the Maxwell relation. Shown here is the Maxwell relation. By using the thermodynamic properties relation in conjunction with the Maxwell relation, one can also write heat capacity in terms of T and S, which is this one.
Hi, my name is NURUL IZZIYAN binti AMRAN, and my metric number is 200298. So moving on to the cyclic relation, it is the triple product rule. Cyclic relation also known as cyclic chain rule or Euler's chain rule. Cyclic relation relates partial derivatives of three interdependent variables. The three variables can be related by a function of the form f x y z equal to 0. So the advantage of using the cyclic relation is it can derive a number of substitution identities which allow one to replace partial derivatives, which is difficult to experimentally measure or evaluate. So by looking at the example, it shows that negative dP over dV at constant entropy is equal to the dP over dS at constant volume times dS over dP at constant pressure. So this is the example of cyclic relation between the three interdependent variables.
Thank you, Aisha and Izziyan, for a wonderful explanation. In conclusion, keep in mind that these are not only Maxwell relations we can find. Indeed, there are other thermodynamic potentials that we can define over a system, each one bringing a Maxwell relation. In addition, there could be other physical quantities that potentials we discuss here could depend on. For example, we might have a system affected by some magnetic field, in which case we will have to take that into account for internal energy, and this will change our Maxwell relation. I hope you guys can take some input from our presentation today. That's all from us. Thank you.